So for our last section of Unit 3, we're going to discuss improper integrals, which you have never been presented with before. We never even discussed back in Calc 1 necessarily what a proper integral is and what would make it improper. Everything you've dealt with up until this point have all been proper. And by proper, I guess, they have all satisfied the fundamental theorem of calculus. So again, we're going to talk about like what makes something improper. All right, so here's our fundamental theorem of calculus, which I often refer to as FTC. You use it all the time, and there are two conditions that you have to have in order to apply the fundamental theorem of calculus. Every single definite integral you've ever been presented with have all passed these two conditions. So what we're going to kind of dive into in this section is what do you do with a definite integral that does not pass these two conditions. So the first condition is that you have to make sure that the function that you're integrating is continuous. So it doesn't have to be continuous everywhere, it just has to be continuous on the interval that you're integrating, like from A to B. So you've certainly integrated things that maybe had a discontinuity at, let's say, x equals 1, but you were evaluating the integral from 5 to 20. And so that's okay. All right, so what we're going to do is sort of discuss that a little bit. Like what happens if our function is not continuous on that interval from A to B? The other thing that we're going to come up against is what if you don't have a closed interval? So the fundamental theorem of calculus states that you have to have this closed interval from A to B. You have to have, a definite start and stop, going from the value of 2 to 3 or whatever. If I make the interval open-ended on either side or both sides, how do I handle that? So we're going to go into both of these problem areas in this particular section. So certainly this is fancier integration, which is why it is a part of Unit 3. And all of your old techniques of integration come into play here. So basic integral rules, as well as basic U substitution, integration by parts, inverse trig, any of those methods can come into play. Trig integrals, trig substitution. So the bigger overarching issue here is that on some of the integrals you're going to be presented with, they're going to be a violation of the FTC. Step 1 is recognizing that. So let's discuss and clarify what I was just mentioning here. So let's go down here. Improper integrals that violate the conditions described in the fundamental theorem of calculus would be what if f of x has some kind of discontinuity within the limits of integration. That is a violation of the fundamental theorem of calculus. So if you have any kind of issue going on, let's say, I'll give you an example. Let's say we're integrating and let's say I go from -1 to 1. That would be a problem. There's some kind of issue here. This function, I'll throw the dx on here, this function 1 over x clearly is not defined when x equals 0. And you've certainly evaluated this integral before, but this would be an example of what I mean. Like there is a discontinuity on this particular function. There's a discontinuity at x equals 0. So that is a problem. So while you have certainly come up with the antiderivative of 1 over x dx, you've never used these particular limits of integration before. Okay, so we're going to discuss how to handle that. The other issue is the idea of not having a closed interval. So what does that actually look like? Let me get rid of this here, just to give myself some more space to write. Is what if we have a limit of integration? I'll just put here, what if a limit of integration is infinity? Or what if it's negative infinity? Or worse, what if your integral goes from negative infinity to positive infinity? That is not closed. So these are your two violations. If you have a discontinuity within the limits of integration or on an endpoint itself, and if you have a limit of integration that is infinity or negative infinity, that is not closed. That is considered open. So if you ever see anything where you're doing the integral from, let's say, 1 to infinity, that's a big glaring sign that there is something wrong. You have never seen that upper limit of integration. And it could equally be something from negative infinity to 0. You have never seen a limit of integration and a definite integral as infinity. And we'll talk about the implications of that, what that means graphically, and how that comes into play. All right, so here are a couple of things, again, to just kind of highlight what I was just mentioning up here. And it goes back to, old Calc 1 integrals. And so if I look at this first one here, this is definitely an integral that you have solved before, similarly. There is no problem with this definite integral. If you think about the function 1 over x, as we described before, now that is not a continuous function everywhere. It does have a domain problem where x is 0. So you have to kind of steer clear of x equals 0. And it just so happens that all of your other integrals that you've done in Calc 1 always did steer clear of 0. Look at my limits of integration. They're from 1 to 5. So this does check off, as far as passing the fundamental theorem of calculus, that gets a big check mark here. Your function is continuous from 1 to 5. They're clearly a closed interval from 1 to 5. And so you can proceed as normal, and you're definitely going to have to do this in this section. Your textbook likes to throw in some old integrals with the new. So this is what would be considered a proper integral. You've never questioned it before because it never really came up. They never deviated from things that satisfied that fundamental theorem of calculus. So anyway, let's go ahead and evaluate it because we should be able to do that. I know that my antiderivative is the natural log of the absolute value of x. I'm just going to evaluate that at 5 and 1, and I'm well on my way to getting my numerical answer here, right? Because the natural log of 5 is some value. Natural log of 1 I know is 0, so there's the value of your definite integral. So everything's fine. It's the natural log of 5. Everything was okay with those conditions. Okay. Same thing on problem number 2, but I always like to distinguish what's happening with our antiderivatives here between problem number 1 and problem number 2. I can't do this enough because it's so incredibly important. But this particular function, once again, this 1 over x squared, if I just think about that in terms of the fundamental theorem of calculus, it also checks out. If you think about this rational function, very similar to the one we had before, again, you have a problem at x equals 0. There are no other problems on this function. And if I look at my limits of integration, everything's okay. I'm not really entering any zone that involves the x being 0 on the graph. I'm looking at the graph from 2 to 3. And that function is continuous from 2 to 3. 2 to 3 is also a closed interval, so everything works out just fine. And so what I'm really doing here is I'm integrating x to the negative 2. And I just want to contrast that with what we had before. Before in number 1, we were using the log rule to evaluate that antiderivative. And here, this is a power rule. So I'm going to add 1 to the exponent, divide by my new exponent, and kind of evaluate that at 3 and 2. I'm going to kind of rearrange that to make it look better for me. So this would be, that would be negative 1/3 minus negative 1/2. So that's negative 1/3 plus 1/2. Let me get a common denominator. That would be negative 2/6 plus 3/6. So again, I have an actual answer here of 1/6. So both of those are things that you've seen before. We have done several times in this class for sure. When you look at 3 and 4, these are your examples of problem areas. These have never been presented to you before, and they show both of the problems. So I want to kind of highlight what the issue is here. So right here on number 3, this kind of sticks out like a sore thumb. You see that upper limit of integration being infinity. That is not a closed interval. So really what I need you to realize is that technically the fundamental theorem does not apply. So I'm going to say this is a violation. Okay, I am going to have a way to handle it, but I need to do so legally. So there's going to be a legal path forward, and I'll show that to you in the next couple of minutes. Okay, on example number 4, what I have is the same function, right? This 1 over x squared. And again, you have a discontinuity at x equals 0, and that's exactly our problem here, that I can kind of see that, well, that's your limit of integration down there. Let me see if I can undo that and go to a highlighter. Right? That is our problem in this particular case. Okay, this function, I'm just going to say f of x has a discontinuity at x equals 0, and that happens to be your lower limit of integration. So again, I'm going to say this is a violation. And when I say a violation, it's a violation of the fundamental theorem of calculus. It does not satisfy the fundamental theorem of calculus. So I'm going to have to do a workaround here. I'm going to have to figure out, how do I actually address these problems? And that has to be step 1. So I can't push this enough as far as like what your job is. Once you realize these problems, step 1 is address the problem. Address the issue, address the violation. And that can't get swept under the carpet. Okay, so let's think about how we're going to address the problem. These are all screen captured from your textbooks. What we're actually going to do is we're going to use a limit process to do it. So we know, and we'll start out with the one with infinite limits of integration, because they kind of stick out, you know, where one of your limits of integration are positive or negative infinity. I can clearly see that as a problem, you know, in what I have going on. Like, it sticks out. It's very obvious that, like, that looks very strange, and that's different than what I've done before. What we're going to do, in a way, is just pretend that everything is fine. I'm going to, keep everything about the definite integral the same, except you notice I changed that infinity to be a b. And so I'm going to say, I'm going to pretend that everything's fine. I'm going to assume that b is just a number, nothing to see here, everything's fine. How you address it is by putting this limit in front of that problem. Okay, so the upper limit of integration is normally denoted as a variable b, and you have to have this limit in front. That's how you're going to handle it. Okay, now, what you're going to do from that point on is you're going to evaluate this integral with this weird kind of variable as your upper limit of integration. You're going to go through the whole antiderivative process, and at the very end, you're going to have to work out that limit process. Okay, so I'll definitely talk about this in pieces. So step 1, you have to address the problem. Step 2, actually evaluate that antiderivative. Find out how to do it. Is it a basic rule? Is it a U substitution? Is it integration by parts? Figure it out. And then step 3 is actually taking the limit of that antiderivative. You know, you're going to use the fundamental theorem of calculus. We're kind of getting around the issue. We're going to address it. And similarly, obviously, you know, if your lower limit of integration was the problem, right? If that is what you see, again, sticks out like a sore thumb. You've never had a definite integral that goes from negative infinity to some number like 5. Okay, so you're going to address the problem first. Before anything is done, before you start evaluating that integral, you need to actually have that limit in front of what you're doing. And again, you're going to come in here and you're going to say, all right, now that I've addressed the problem and I recognize it, let me now evaluate that integral. I'll find the antiderivative. I will actually start to try to use the fundamental theorem with that antiderivative, and then at the very end, this problem turns into a limit problem. Okay, your third bullet here is one that looks incredibly treacherous because it's doubly improper. That's an actual term that is used here. You see your limits of integration are both problems. You're talking about the area under some function f from negative infinity to infinity. It's an infinite region. And so we want to try to figure out, is there any way to evaluate that? Is there an answer to an infinite area? Shockingly, sometimes the answer is yes. But you can't handle something doubly improper. You need at least one of your limits of integration to be fixed, anchored, and good. And by good, I mean real. So what you're going to have to do in this situation is create two smaller problems. One where you start from negative infinity, of course, and you stop somewhere. That c can be any number. It can be 0, it can be 1, it can be 14, whatever you want. But then you're going to add another integral where you start up where you left off. If you happen to choose 14 for your upper limit of integration here, you're going to choose 14 for your lower limit of integration there, and then go all the way to infinity. So it would be a combination. To do this third bullet, you would have to execute, rewriting the first integral here in terms of what you see for number 2, and rewriting the second integral as what you see in bullet 1. Okay, so you would need to address both of those. So we have to work on it. Okay, now, when it comes to actually coming up with a value, we have some new lingo, and this lingo is going to also be present in Unit 4. If it turns out that you evaluate your integrals and you actually get a number, after all of this process, you actually get some kind of value, some kind of number that's real and fixed, then what we say is that the integral converges. I'm going to say, therefore, the integral converges to that number. Okay? If it turns out that your integral does not equal a number, that you've gone through everything that you had here, let me get rid of the not equal to there. If it equals a number, then the integral converges to that number. If it turns out that you do your whole integral work and it turns out that it's evaluating to infinity, well, that's not a real number L. That's not a value that you can see and plot on the number line. If this is what happens to you, really, you're basically saying the limit does not exist. So what you're going to have to say is that the integral that you were evaluating diverges. It means it has no known value, and it's certainly not something that you can plot on a number line. So those are your two conclusions of what could happen. Now, if your limit doesn't exist in any way, maybe it equals negative infinity, so I'll put a plus or minus on here. Maybe for some reason the limit just doesn't exist for a variety of reasons that limits don't exist. If you have anything strange going on, then you say that the integral diverges. The only way you have an integral that converges is if it equals a number that you can plot on the number line. Okay, and this little kind of statement down here, certainly it's worth you reading. It's certainly a part of what's going on. Take a look at this. This is what's kind of what's explaining what I just said over there. The improper integral converges when the limit exists. Otherwise, it diverges. But this third case, what do you do if one of the integrals diverges and the other converges? Well, if one of them diverges, the whole thing diverges. That's pretty much what that statement is saying. So if I do the first integral and it diverges, I don't even care about the second one. Okay, because remember, you were investigating this whole thing as one colossal whole. So if one part falls apart and diverges, then I'm done. Okay. Now, when we have integrals with infinite discontinuities, we're going to take the same approach. As far as we're going to identify the problem, you have to recognize that there is a problem, and then go from there. All right. So what you're going to see me do is kind of use this process of identifying whatever the issue is. So let's say in problem number 1, you have some kind of discontinuity at the upper limit of integration, that if I go back in here and say, okay, well, there's some kind of discontinuity at b, what you need to do is actually throw a limit to address the problem. Same thing, you are then going to come in here and you're going to evaluate that integral, keeping in mind that there's a limit out there. You're going to come up with the antiderivative. At the end of the day, your work turns into a limit question. If it equals a number, it converges. If it does not equal a finite fixed number, then it diverges. Okay. Similarly, I guess I should say, if your discontinuity is at your lower limit of integration, which could equally happen, your first step is identify that lower limit of integration as being a problem. This is your way of addressing the issue and being permitted to continue on. All right, from there, you're actually going to evaluate that integral and turn it into a limit question. All right, now, the same part C is happening, or the same, I guess, third bullet here is happening in this particular stage of the game as well. If you happen to have an issue inside the integral, inside the limits of integration, where let's say you're going from 1 to 4, but there's a discontinuity, let's say at x equals 2. You would have to break up the integral from 1 to 2 and from 2 to 4. And in both of those cases, you would have to make sure that you're addressing the problem areas, that you would have to address the discontinuity at 2 as the upper limit of integration, and you would have to address the discontinuity down there as the lower limit of integration. Okay. The same clause happens here that happens in the first box, that if you have to handle two integrals, if one of them falls apart, the whole thing is a train wreck. Okay, so if one of them diverges, then you would say the entire integral you are presented with diverges. Okay, so it's worth taking a look and looking that over and reading it. Now, I'm going to execute some example problems here to show you what I mean. I use slightly different notation than you see here, but we'll walk through that as we go through some of these example problems. The most important part is that you identify the problem with the fundamental theorem of calculus. The very first thing that you should have on your paper after you've figured that out is a limit. Okay, you must have a limit on your paper to evaluate any improper integral. That has to be step one.